All right, so what's an SRF cavity? The basic idea is very simple. We use these devices to accelerate charged particles. Forced by electric field on charged particle, and that can be used to accelerate the charged particle. Typically, oscillating frequencies of these F fields are a few megahertz to a few gigahertz. That depends on the cavity, on the application. The highest achievable gradient is sometimes important, but often it's not. We care about other things which are not directly related to the maximum gradient, and that really depends on the kind of accelerator which is using that to accelerate the beam. And in many cases, there are different requirements which can be competing. So I have this beautiful slide here, which will make this very clear. So on the left side, there's some machine parameters like the beam current, whether it's CW continuously on or pulsed, what kind of beam power could be delivered at the end. So that is whatever is needed to drive the science of just the applications. That translates then in some of design parameters for cavity. Again, details of matter here. And then this impacts things like the cryostat design for the cavity, the input coupler, which is used to couple power into the cavity. So all these technical components of that gets derived based on what at the end the accelerator is supposed to deliver. There are two basic types of cavities. One is called a standing wave, and one is called a traveling wave cavity. And as you can guess from mechanics, that's how they look like. If you plot the field for the time in the standing wave, the fields form standing waves, and the traveling wave fields form traveling waves. SRF cavities use mostly for now the standing waves. Non-conducting cavities often use traveling waves. In the traveling wave, you get a benefit because your charged particles here, of the green, travel with the crest of the field, so they're always in the maximum accelerating field. Whereas in the standing wave cavity, that is not true. There's some averaging effect. Different machines with accelerators have very different requirements for these cavities. So, for example, there's some which operate in pulse mode. So the field is only on for short pulses, can be a microsecond, can be even shorter than that, but again, depends on the application. So there, the gradient often can be very high in these applications. There we care about the maximum field, or the energy gain per length, RF power. Feeding the cavity can be very high, but it's pulsed. But within the pulse, it can be very, very high, often many megawatts. And there's a thing called HR damping. I will come back to that later on. That is not so severe requirements on that. That's very different for other machines. So for example, a high current energy cover Linac. Yeah, the cavities are on all the time. The gradients are more moderate, around whatever 20 megawatts per liter or so. Their power is still low, but higher modes can be very big issue. So depending again on the machine, different parameters can be the challenging part. Can reach high gradients, can support high beam currents. That really depends on the application. There are different kinds of cavities and there are different functions. So there are those who use what we call the fundamental mode. They use for beam acceleration, for the fundamental energy to the beam. I'll show you some examples. There are so-called third harmonic cavities. They are used to do some advanced things to these bunches of particles. I will show you a bit about that later on. Then there are dipole cavities. They have electric field switch on transfers to the beam direction. They can be used to kick the beam, to twist the beam. And then there are also for SRF guns, which use, again, these kind of oscillating fields to accelerate the particles right behind the photocatalyst. Here's some examples. So there are SRF cavities used in, which has a case on that. The SRF cavities used in storage rings, like the one we have on campus. Awesome. So there, the main goal is to provide energy to the beam. So they accelerate the beam. The other thing, they actually make sure that the beam is stable over time, called lifetime, that basically the particles stay in the beam and are lost. So that's what the cavity is doing there. They also care a lot about what happens if the beam goes through these cavities, like shown here, because they're very high beam currents. So again, these higher modes, they can be severe issues for these storage rings. She called that touch current. So often these cavities are quite gigantic. because that minimizes the bad interaction of the cavity with the beam. For Linacs, like shown here, on top flash, SRF, plate neutron source, and oak bridge at the bottom, there is SRF cavities in the Linac accelerator. And these are operated in pulse mode. So they like to have a decent energy gain for length, just to keep the Linac at a finite length at reduced cost. So high gradients are often used there. High here means about 25 or so megawatts per meter in pulse mode. Then there are these cramp cavities. Those are the ones which have transverse fields. They can have a bit of funny shape. They're no longer completely circular, but deformed. They're different designs. But in colliders, these are used to twist the beam. So think about the collider. The particles might be coming in at what's called a crossing angle here, in this direction, say. But if they then interact here, you want to have the maximum interaction. And you can achieve that, you can increase that by twisting the bunches such that they interact as much as they can. So for that, transverse fields are used. So here the electric field runs transverse to the beam direction, not longitudinal. These cavities can have really funny shapes, as shown here. They look very different than the ones you might have seen in animations earlier this week. But it's here. The matter can, they have some eigenmodes you can excite, which have electromagnetic fields oscillating. And in this case, the electric field runs transverse to the beam direction. There are also special SRF cavities used for particles which have not the speed of light. So, for example, ions, protons initially, but they're much slower than the speed of light. And again, for those, elliptical cavities would not be feasible. And again, you use a different kind of metal can, which looks a bit like this. The inner conductor here, the outer conductor, the beam goes to this, the gaps here, that's where the field points longitudinal for acceleration. These are what we call the low beta cavities. So here's a picture of how the mode looks like, the typical mode in a elliptical cavity or here pillbox cavity, which is used for acceleration. So here in this pillbox cavity, the beam will go in this direction. You see the electric field points longitudinal, and then the magnetic field a circle around that. So an elliptical cavity then looks like this. Electric field again longitudinal, the magnetic field a circle around that. So the magnetic field is highest here at the crater of the cavity. Or again, the beam goes to this like this. To get the crater, that is where the local surface field is the highest. So that's what we care about. That's where the superconductivity located first. The electric field, however, is highest on these surfaces at the iosis here. Those are the ones where we need to be really careful with cleaning them to make sure there are no field emitters sitting there. Most of the cavities we're using have multiple cells, shown here. So here's a 9-cell cavity, like for the IRC. Again, like red dot here, these are charged particles going to that. And what's used here is like a coupled pendulum. But if you have n coupled masses, then you get n modes. So same thing here. The one we use for acceleration of these 9 modes here is the one with the highest frequency. That's a pi mode, where the direction of the field alternates 180 degrees from cell to cell. So that's what's used for acceleration. You can model that with an LC circuit, coupled LC circuits. So when the beam goes to that, the field oscillates, and if everything works as it's supposed to be, you can see why the bunch here goes through the cavity. Each time it's in the middle of the cell, the field points in the same direction. So the bunches, the charged particles get accelerated in each cell. There are a few typical things we talk about. One thing you've heard is the accelerating voltage. So that's the energy gain for a charge, such a cavity. That's what we mean by voltage. I would think about 25 megawatts per meter or so. That is then the voltage divided by the length. Other things you might have heard us refer to is a thing called the shunt impedance, which is the voltage squared over 2 times the dissipated power in the walls of the cavity. And that way, the coil factor of the cavity is omega 2 pi f times the stored energy U divided by the dissipated power. If you take it to divide the shunt impedance by the coil factor, you get this R the Q factor here, which is also something you would hear frequently used. And that actually at the end turns out to only depend on the shape of the cavity, not on the frequency, not on the size, just on the shape. Where the charged particle, like shown here on the right, goes through an SRF cavity. and leaves behind what we call a wake field, some electromagnetic field. If you look at the frequency content of that, that can go to really, really high frequencies, as shown on the top left graph. The shorter the bunch, the higher the frequencies left behind will be. They can easily be hundreds of gigahertz. So while the beam goes through a cavity, at least behind this wake field, there's unwanted electromagnetic field. So that's something which can then impact the next bunch. So one bunch went through here, right? It's behind all of this. The next bunch comes in, it sees all these fields, which means there can be fields pointing longitudinal, there can be fields pointing transversely, and that can impact the beam quality. So we don't like this. We don't like this field left behind. So that's something we have to do something special to suppress that effect. And that is called high downward damping. So there's special antennas or other things which are used to suppress these fields. They still get excited, but we're trying to extract that power as quickly as we can. There's no resonant buildup, because that would be the worst if all the bunches go through these cavities and start to excite all these unwanted modes. So some of these antennas, like shown here, they're sitting between cavities, sticking into the beam pipe. They couple to these unwanted modes to suppress them, to reduce the quality factor. You can do the same thing with these waveguides. Again, that extract power at higher frequencies. You can have absorbing rings here, like this one in the beam pipe, which again interacts with these unwanted fields to suppress them. The trick is you have to do all of that without impacting the one mode we like for acceleration. So one mode we want to have quality factor like of 10 to 10, 10 to 11, higher the better. For these unwanted modes, often we try to suppress the quality factors to something like a few hundred. So that is often a challenge if you think about the high beam current operation. All right, so why do we make this superconducting? So the material of choice of all know is niobium. So far, we're trying to change that. Put the temperature level to K. And by making them superconducting, we use the lowest high frequency mode, so typically around a gigahertz frequency or so. And that's the one we use for acceleration. And everything above that we don't like, we try to suppress. So by reducing the water dissipation, by making the water superconducting, we get several benefits. It allows us to go to high operating fields, especially in continuous operation, much higher than what we could ever do in a copper cavity, because the copper cavity would just melt. Very high power efficiency, like green accelerators, energy sustainability. It will help with that. But it also allows us to just tailor, optimize the cavity design, taking other things into account. So for normal conducting cavities, you try to minimize the wall losses by optimizing the shape. And that's important. For the SRF cavity, the wall loss is important more. You can sacrifice some of that by designing cavities which, for example, optimize support high beam currents. One example of a really efficient accelerator is one we have here at Wilson Lab, which is our injector of the ELL. Quite a while ago. So that thing actually ended up operating with really high beam currents, around 70 plus milliamps, which I think is still the world record for this kind of operation. And with that, we achieved something like 50% AC power to beam power efficiency. So 50% of the water power went into the beam. So that is quite amazing. That's something you can only do with SRF cavity. I don't have to talk about superconductivity, right? We all know what happens there. So let's skip that. But when we talk about SRF cavities, you always see these quality factor Q versus Q squares. So Q means proportional to 1 over loss, so high Q is good. So we try to achieve high Qs. And also we try to go to high fields, high energy gains. So going in this direction here is good. High Q, high fields. So here's step by step how an SRF cavity gets made, at least usually. So it starts off with sheet metal, as shown on the left. It gets formed by stamping into half stars or so, sub-assemblies. Then all of that gets welded under vacuum to an electron beam. So you use an accelerator to build an accelerator. Because if you do it in air, it will oxidize the aluminum. You wouldn't get good welds. Then typically there's some baking, there's lots of nasty chemistry to remove the first 100 or so micrometers from the surface, because that is all damaged from the fabrication process, especially from rolling the sheets. Then we clean things in the clean room, more baking, more chemistry, other things, coatings, all of that. So very short history. So it all started in 1908, where Ohms liquefied helium. And then just 3 years later, right, he showed that the connectivity is the thing. So that's from the original notebook here with mercury. And then 1961 was the first paper proposing to use SRF materials to make RF cavities. That is here the first paper. And then just 4 years later, actually, work started at Stanford, and they were actually using lead on copper at this time, not iridium, but lead on copper. So 64, the first high cavities, SRF cavities, and then just a year later, the first acceleration of electrons with these cavities. Here's how one of these really early cavities looked like on the left. And then on the right is one of these Q versus E graphs in computer units, where Q is the Q. You can see you get Q of 10 to 10 at that time only. There's a caveat here. You read carefully the temperature is 1.25 K. That's not where we operate normally, because that would be insane. The field here is an Ørsted magnetic fields. I didn't get really high fields at that time. Then early 1970s, the first accelerator was actually built at Stanford using SRF cavities. You can see the cavity on the left there, 1.3 gigahertz. You might have heard this frequency before. The field they got was something like 2 megawatts per meter. No fields going off day standard and no beam current. They were limited by a tech called multiplexing, where electrons get emitted, they bounce back and forth between different sites in the cavity and multiply, like in a photomultiplier tube. Yeah. Here are some other cavities which came later. 1975, the first SRF cavity in synchrotron in the ring accelerator here at Cornell. And then the first SRF cavity in the storage room again at Cornell. You can see the shape here, not elliptical, it's still box shape, which was part of the problem. We had to fix that. The elliptical cable shapes actually help with this multiplexing effect. So over the decades, step by step, we learned how to improve these cavities, their shape, their preparation to get closer and closer to the ultimate limit of myopia. And with these improvements over time in performance of these cavities, there was basically an exponential growth in their usage. So it's shown here as a total installed voltage versus here, you can see it's an exponential growth, which still supports to today. So for the future, we obviously like higher gradients and especially higher Q, because for many applications, the cryogenic plan is just insane. So higher Q will help a lot with making them become reality. So as we know, you can get to higher Q by reducing the surface resistance, and you can also reduce power consumption by operating higher temperature. Either way, it's a good way. And all we need to do is optimize the first 100 nanometers of the surface. That's how far the field penetrates into the superconductor. That's really all that matters. And that's what our team was working about on to optimize the first 100 nanometers or so. All right, I will skip the examples here because you've heard about niobium and you've heard about iridium. So we'll end just with some pictures here from my lab. If you haven't gotten the tour, let me know. I'm happy to show you around. So we have all the infrastructure on the left, electron beam guiding machine to make cavities, then the clean room to prepare them, to clean them, and our test pits here to test these cavities from pretty small to pretty big here. The largest we had ever tested. That was for a potential neutron collider. That's the beam guiding machine. That is going to do the chemistry, the etching of the cavities. That's one of our furnaces for the baking. That is the tin insert, we do the coating. This is again from the clean room, where we also sometimes put together whole accelerator sections. Each of these little things here as a cavity. See one here, one there, and so on. So the string. That's more the clean room where we do the cleaning. We call this high pressure rinsing. It's like a car wash system, high pressure system with very clean water. Some more inserts here. Again, there's a test area with a big holes in the floor with fire cans in there. All doors. That's where the testing happens. We're building currently a CVD system, which you have on the board. That's commissioning now. We can show you that. And finally, we thought about applications of these. So here is the conduction fluid coil module. On the left is designed, the single side cavity sitting in there. Cooled from the top with converted coil coolers. There's no liquid helium, no liquid nitrogen involved whatsoever. It's all just cooled via thermal conduction. That is how the coil module looks in here. From the outside, this is doing assembly from last week. You can see the cavity here. This would be the input couplers to couple power into the cavity. That's the beam line here. And then this here is just the final vessel that one vessel. So we're putting that together, should be together in a couple of weeks, and then we're going to test that. And I think my time is up. So any questions?
When we have normal RF cavities, they need to be like conditioned, and we have breakdown happening.
Yeah.
I imagine if I have breakdown happening in an SRF cavity, it's pretty not good.
We would be in trouble, yes.
Is this not a problem we occur because the fields are not high enough, or because they're cryo-cooled?
But the fields are they're decent fields, but I think the way how we clean the cavities they are different. Like we go through clean rooms, we high pressure rinse these cavities. So we actually limited much earlier.
Okay.
By field emitters. So these cavities typically are clean. There's no field emission, there's no breakdown whatsoever. Up to the fields we run at, whatever it is, 45, 50 megawatts per meter.
Okay, and then the last question, Michael.
Why are for the cavity for the neon, why is it so much bigger than the normal one?
So that's to capture the beam. So you start with a beam, photon beam hitting a target. Then you have to capture the neons behind.
Oh,
So the beam is big. I need the big beam pipes and the big cavity.
Here's a short question.
Maybe, I was just wondering, you're talking about, you have to do a lot of these things in vacuum because of oxidation. How do you transport it to prevent that?
So they always get vented, they always oxidate at the end. But we're working on preventing that right with the gold coating, for example. So that would prevent that oxidation.
Okay.
All right, let's thank Matthias.